All right. For those of you on YouTube, welcome back. For those of you in person, know that we've been talking already. Anyway, we're going to continue with the exciting lecture on factor analysis. We're going to finish the conversation today talking about model estimation, which probably won't go all that long because I am doing my best to keep this only on the topics that are, to me, most important and relevant. Not to bog you down on some of the esoteric details, which I love, but most of you are not here for the esoterics, right? You're here for how to do this so you can use it in your work. So after we get done with the lecture part of this, just like Lisa Hoffman does, I have a handout, an example that we will go through doing a factor analysis example as well. And at the end of the day, you should be able to have everything you need to do that homework online. Okay? Stop me if you have questions. But here we have a two-factor confirmatory factor analysis model. What does a circle represent? A factor, something you didn't measure. What is a parallelogram? That's right, right? What does that represent? An observed variable. Yeah, this is, again, this distinction is more common in the social science version of path analysis. If you get into directed acyclic graphs, I don't care, whatnot. And then, of course, there's your eye of providence, the number one. I don't even know if eye of providence is something. I don't even know there's something mystical about it and historical about it, and I know nothing about it. I'm just using it by definition. So if that is something I probably shouldn't use, can you give me advice? Anyway, it does creep me out. The back of the dollar bill with the eyeball on it, right? Oh yeah, National Treasure. Was that in that? Yeah, that was a long time with Nicolas Cage, right? Yeah, National Treasure. That was great. That was back when people cared about Nicolas Cage. Is he still doing movies? Yeah, that's good. Okay, I don't know because that's good. Yeah, I'm all for comebacks. I don't watch movies. That's the thing. Actually, if you're going to be like, have you watched a movie? I'll give you a 99.5% chance the answer is no. Or if I did, I hated it. So I can't do movies very well. I'm sorry. I've never been able to. But those are the means. Thank you. Going back to the topic. So what we have here are a set of data. We have parameters to estimate intercepts, factor loadings for both factors. We have unique variances for each of the error terms themselves. And we left off last time with where do the numbers come from? A black box. Turns out, for me, learning about estimation in these models was wonderful. If you're ever looking for a place to learn about estimation beyond just least squares, linear regression, start here because it's wonderful, meaning, yes, it's technical, but it's not nearly as bad as it could be. And there's a lot that sort of are easier in the case where we assume everything is normally distributed, which we shouldn't, but we have to do it. But here's what we have to estimate. We have that model that I had before, a model with 2 correlated factors and 6 observed items. We have F1 was being measured by the first 3 items, and factor 2 was being measured by the last 3 items. If we fix both factors to have a mean of 0 and variance 1, remember that's standardized factor or z-score factor identification. We talked about identification methods last week. Then what we have to estimate are all the intercepts, or 6 intercepts, all the factor loadings, 6 of them, and 6 error variants, or unique variances. So there's 18 parameters plus 1 factor covariance between the 2 factors. So 19 total parameters. The item parameters themselves are, if you're thinking of this from the perspective of a multi-level model where there might be fixed and random effects, in this sense, the item parameters act as fixed effects, meaning that they are constants. They're like regression slopes. They're inference about a specific item. So each item's intercept relates only to that item itself. It's okay if missing data leads to different numbers of total items across people. That's the other thing I should note. What's happening using maximum likelihood, or robust maximum likelihood, is that for each person, and this is going to show up on the next slide, but just think of it this way. The 6 items, and with the assumptions of factor analysis, just like in path analysis that I've taught you up to this point, we're assuming multivariate normal, a multivariate normal distribution for the 6 observed variables. Remember, multivariate normal there's 6 means and there's a 6 by 6 covariance matrix. If a person only gives you 5 items, though, the multivariate normal for 5 can be used, because what we end up doing, instead of saying, let's imagine they don't give you item 6 as a response, we just form a multivariate normal with what they did give us. So instead of having a 6 mean mean vector and a 6 by 6 covariance matrix, it could be a 5 mean vector and a 5 by 5 covariance matrix. So in many ways, what happens in missing data under maximum likelihood is that we're basically skipping over what was omitted. And so long as a person gives you one piece of data, you can use that one piece of data, right? So it is nice. Turns out, you might think, wait a minute, F1 and F2, what about those? And I've been leading up to this point talking about this already, so you probably aren't thinking that because you're all hanging out and enjoying what I have to say, especially those jokes. But F1 and F2, the magic of this is you don't have to estimate them, right? They're not part of the model. Actually, they are part of the model. I should just scratch that part. They are part of the model, but they're not part of the estimation function. Let's make a distinction between the two. So the estimation function, we can write a likelihood function without the latent variables. This is actually, for those of you, the 3 of you who are part of my neck of the woods, my corner of the research world, this is a very fundamental part of latent variable models as well, just as fundamental as local independence. So the rest of you, you're welcome to listen, but I'm going to speak to this side of the room here. We have to not be able to estimate, we have to write a likelihood function without latent variables. The reason for that is, if you think about how our statistical properties behave in maximum likelihood, we often say as n goes to infinity, right? And the reason for that is, in models where we don't have latent variables, you can think of it this way. As n goes to infinity, the sample size is increasing, but the parameters are constant, right? That's a good situation to be in. In this model, though, every time n goes up, we have 2 additional parameters, if we think of those as parameters, right? So as n goes into infinity, the number of parameters is also going to infinity in this case. That's a problem. So latent variable models to be estimated using maximum likelihood have to write a likelihood function without the latent variables in it. The name of this problem relates to a paper by Jerzy Neyman and someone named Scott. I don't remember her name. Her first name now, I'm blanking on her name. But the Neyman and Scott problem, it goes back to like the 1940s. Understanding that if you create a model, try to estimate a model where you have parameters increasing as a function of sample size. In our case here, because every person we get needs more factor scores, we are not guaranteed for that model to achieve some of those good properties that maximum likelihood would have, which would be consistency being one of them. They're just not consistent estimates. Consistency is the property that as n goes to infinity, you converge in probability to the true values, right? So that's bad. That's really bad. So it turns out, for our model, the factor scores themselves, in a multivariate normal, we can do some tricks of math, and lo and behold, we get a likelihood function that does not have f anywhere in it. And part of that likelihood function uses that equation from before that I showed you, the matrix math. That is the equation for the covariance matrix, right? So, other ways of looking at factor scores. We can think of these as random effects, meaning that they are believed to have some type of prior distribution to them. Another way of random effect thinking, another way that we think about random effects in a statistical context are effects that describe a population, usually through variance components. You see this in mixed models or multi-level models, in that the comparison of not random versus fixed effects. A fixed effect in a linear model, not factor analysis, but back to the linear models, fixed effects, if you have 3 groups of people and you want to see group differences, those are fixed effects, meaning they're specific to the groups. If you have 300 groups of people and you want to see how much variability there is in their effects, that is now you take a random sample and you try to quantify that variability. For us, with factor scores, we took a random sample of individuals and we're trying to quantify how much variability there is between people in this sense. Although that quantification is a little weird because we sort of fix the variance and mean up here. And that's why it's not a perfect mapping of understanding of random versus fixed, but there are random effects in that sense. That makes sense? Okay. So you don't need, we don't need the factor, ironically, this is the beautiful thing about this, right? If we needed to estimate the factor mean, so if we identified the model where let's say we want to estimate the factor variance. Do you remember how we would be able to do that before? A marker item. So we would reduce the number of factor loadings by 2 in this case, 1 for each dimension. And then we'd have 2 variances here, right? It turns out when we do that, we still don't need the factors to get the variance of it. Because the factors themselves, again, we'd write the likelihood function. The likelihood function has the variance in the likelihood, but doesn't have f. So now it's another parameter to have to search for. Okay? So, all right. That's me and my discussion. Why are you not moving forward when I want you to? There we go. So, here are the goals of maximum likelihood. I'm assuming at this point you probably haven't had much maximum likelihood. I don't think Lisa describes it much in generalized. So I'm going to give you a little bit more here. So maximum likelihood. The goal is to get the most likely values for each known parameter in our model, which we call estimates, or maximum likelihood estimates, MLEs. Sometimes they're called that. Most likely is in quotes there. We'll talk about what it means by likely in a bit, but that's literally the translation of maximum likelihood, maximum to most, likelihood to likely. We also would like some type of index of how accurate or how much variability there is in those parameter estimates as well. We call those the standard errors. Right? So everything that comes out in the model. And then sometimes we actually then at the end for our model itself, we would like to get our model fit indices. And how this all happens starts with the idea of multivariate normal distribution. And if you forgive me for a moment, I'm going to just describe univariate normal. And this will be a few slides. I like talking about this. I want you to see this because it does help understand the process of estimation as you go forward. It also helps you understand what is possible because maximum likelihood that I'm showing you right now is relying on normal distributions. But every distribution has a likelihood function. So when you understand that, if your data don't seem to follow a normal distribution, you find a distribution that does, and you can still use maximum likelihood. That's the nice thing about ML. Okay, so the univariate normal distribution, the bell curve. For better or worse, there it is. Right? What the PDF tells us. So this is the range of where observations or data might be. This is how the relative likelihood of observing that. So how we read this plot would be, if x equals 0, on the blue distribution, we'd say that is the most likely value for it. Right? The actual number itself, in this case, is relatively meaningless. You can ascribe meaning in some cases, not here. Right? It just means if I have a value of 0 and Michael has a value of 1, and we want to say which one was more likely, we look at the height of the 1, we look at the height of the 0, and the one with the higher value was more likely. Right? And how we do that is the following, right? We say, although this says x, pretend this is y here, but basically we'd say, what is your value of your observed variable? That goes right here. And with a given mean, right there, and a given variance, we can tell you how high that curve is. Right? So if we know the mean and the variance of a distribution, we can say how relatively likely each observation was to have happened or to have come from that distribution. Sound good? Now, here's the flip. When we do this in practice, we don't know the mean and we don't know the variance, but we know all the data. And we can use the function the same way. So what we do in practice is by saying the following. When we know what y is, what's the mean that's most likely given all my data? Or what's the variance that's most likely given all my data? And it still uses the same function, right? Now, this function is built for one person's y, right? We have to go expand this across all of the people, right? So we have to take what's called a joint likelihood. But when we do that, we have a whole bunch of y's, a whole bunch of equations, and only two unknowns in this case. And we can solve for it. Now, how we solve for it gets a little complicated. But that is what we do. So that the idea is this: you can go and figure out, this is data from Excel. There's a function in Excel called normDist. And yes, when I first started teaching this, back when I started my career, I was using Excel. Now they're like, yeah, just use rnorm or dnorm and R or whatever else. But the idea still maintains, right? The idea is that here, if we plug in a mean and a variance, right? Actually, pardon me. These are the values of the outcome. Under this mean and this variance, these are their heights. Under this mean and that variance, these are their heights, right? And so what we're looking for is to figure out the value of the mean and the variance that maximize our likelihood function. So multivariate normal works the same way. And I'm just kind of sketching we're not going to go too deep into this again. I'm just going to keep it surface level. Again, we know what y is. We don't know what mu and sigma happen to be. Okay? In our data, though, we know this formula right here is sigma. That's the one I told you not to remember. That's okay. If anybody does get a tattoo, I want to hear about it, though. But what does it tell us, though, right? Basically, we're going to do this. Our system in the computer, God, I sound old. It's all computer. But what we end up doing is to use this function. We know what y is. We need to plug in the mean vector, and we need to plug in the covariance matrix. The mean vector, we know from our algebra and our math, that is formed by our item intercept parameters. The covariance matrix is formed by our factor loadings, factor covariances, and unique variances. That's what each of these matrices are. Capital lambda is loadings, capital phi is factor covariances, and psi, capital psi, is our diagonal matrix of unique variances. So think of what happens here. What Laban will do is we'll start off and they'll say, I'm going to make a random guess as to what all of our mean intercepts are, our loadings are, our unique variances, and our covariances. Let's just randomly guess them, right? So once we have all those parameters, we need to make them into a mean vector and a covariance matrix. So we use these formulas. Got that. And then we plug in each person's data right there. So each person then gets a likelihood. We could take the log of that and sum it across people. That's the likelihood of all people. So for every set of mean item intercepts and every set of item parameters in the model, we have a likelihood that goes with it. So now, what Laban and what we end up doing is in mathematics, we're searching for the values that go into mu and sigma that maximize this function. And that search process, there's all sorts of cool ways of doing it. There's not cool ways of doing it, but you can think of it this way. I'm going to try out a different mean vector. I'm going to try out a different set of loadings and so forth and get a new log likelihood. Right? So you just try out values. You can think of it as just a search. And we're searching for the values that maximize this function. Now, there's calculus we can use, some really cool things with calculus as well. This is, by the way, the sample log likelihood. So this is the sum of the log of that function from before. And let's see what I have here. Nope. So what will happen in R is there is actually a built-in R function called optim. I don't know if you've seen that one before. Optim searches a function for a maximum as a set of parameters. It uses methods you may have heard of in other classes, depending on how mathematical your classes are, something called Newton-Raphson or Newton's method or quasi-Newton. There are ways that we could use calculus to take derivatives of this likelihood function to find the peak. So if you think of it this way, a lot of maximum likelihood. Remember the contour map discussion we had a couple weeks ago? Imagine we have the weirdest game ever. It's like a Mr. Beast episode. We're going to helicopter people in blindfolded onto a mountain. And they have to keep a blindfold on, but they have to find the peak of the mountain. They have to find the summit. The worst Mr. Beast episode ever, right? YouTube episode. But that's basically what maximum likelihood is. You've been blindfolded and dropped into a mountain with your first estimates. It's going to search basically in each dimension of the estimates to see where the steepest slope is, and you'll walk towards it. If you think about you on a mountainside, how would you, if you had no sense of vision, how would you tell where the peak would be, right? You'd probably search around and look where the step is going up, right? That's what happens mathematically here, is that using calculus, we can figure out a set of new parameters that increase the likelihood, move up the slope of the mountaintop. And eventually we get to a spot where our new parameters that we suggest don't change the elevation very much, right? So eventually you're like, oh, is that higher or is it lower? I can't quite tell. It's actually what we call convergence. When the change in the likelihood is not much based on the change in parameters, we terminate the algorithm. And those are considered our estimates. So that's how maximum likelihood works. The magic of this to me is that we can write all of this without the factor scores. So we get around that, what I will call the Neyman Scott problem, the problem of having parameters going to infinity while your observations do. Questions on maximum likelihood? Turns out it works the same almost in any statistical context. Yes, the likelihood function exists. Those are always what maximum likelihood runs on. What varies from this class to multi-level is how we form each of the parameters that go into the likelihood function. Right? In our class, we had that one formula, which I could have wasted read David Kaplan's derivation of how that came from. That's good. I wouldn't call it waste of time, but I could go down that route, but we can derive it. In a multi-level class, this thing doesn't get formed that way. Not exactly. Kind of close, but not exactly. Right? It gets formed through a combination of your variance components, your level 1 and level 2 variances. You may have heard things called like a G matrix before or an R matrix. That is how we form it. So your model will do different things to these sets of parameters, but the process of maximum likelihood just finds a maximum of that function with respect to those parameters. So it kind of embeds a function within a function to do it. Anyway, it's kind of cool. Yeah?
Do you different programs because of how they use our new set of parameters land on different types of points? That's very often.
It can happen. So it turns out the question was, do different programs produce different results for the same data? Is that a good way of putting it?
Yes.
So yes. In models that use normal distributions, if there are differences, they're often very small because the methods used to do the calculus behind this are very regular, and they usually rely upon very stable numerical libraries that have been around since the space program's inception in the 1960s. So if we run the models in Lavon, we run them in M+, clearly different people wrote those algorithms. The results usually converge to as many decimal places as can be shown on the screen. When you go outside of the the multivariate normal version of maximum likelihood, that's where differences really change. And so in our case, that would be if we're trying to do maximum likelihood, full maximum likelihood on categorical data. So we can't use this. The only reason we're using a multivariate normal here is we're making that assumption about all of our observed responses. If we are saying, no, wait a minute, these are actually liquid items, I need to use an ordinal or a multinomial model of distribution, now we can't actually express this likelihood without the factors unless we use an integral, a numeric integral. And methods for numeric integration are not as regularized and will vary widely. So what you'll end up seeing is, and actually this is a funny question, so I'm rambling on about this, but I'm just trying to give you the sense of it. So for years and years, we've used this homework system. Lisa's really used it. I've sort of begrudgingly tried it and occasionally like it. And the biggest pain that we had was, particularly in the early classes, some of you want to use data, some of you want to use R. How do we get the same answers to check to the same tolerance? And again, for models that you'd see in like linear models, And most of the normal theory-based factor analysis, path analysis, pretty consistent. As soon as you switch over to a generalized model, it is off and off big time. Can be off big time. So that is a little concerning, and that can be problematic. Does that answer your question? All right. Other questions about this? All right. But turns out maximum likelihood is, and likelihood theory is a really powerful statistical concept. It's why we have a lot of trust in our numbers as we go forward. But the other thing that can happen is when the model converges, right? When we find that peak of the likelihood function with respect to the parameters, what we can then do is take versions of our likelihood. We can basically look at the curvature of the likelihood function to describe how much variability there is in the parameters. When I say curvature now, those of you who've taken mathematics and calculus, you are probably thinking, yeah, lines that are tangent.
Derivatives.
Exactly. So it turns out if we take our log likelihood function, right here. Now this is an oversimplification because really what we need is to take this thing and differentiate it twice with respect to the parameters of interest. Right? So what does that mean? Not sigma, but think item one's first factor loading. Right? So we'd have to go into the first and second derivative of that. The matrix of, so these are called partial derivatives. Matrix of second order partial derivatives, sometimes called a Hessian matrix. That thing, if we were to take -1 times that, we get the information. Actually, yes, Hessian matrix times -1 is information matrix. And basically that thing, 1 over information, is our 1 over the square root of information. So the diagonal of that matrix gives us our standard error. So, no, better not be negative. Beyond that, way to think about this is because of maximum likelihood, we can tell how much variability we have in our parameters. Because it really comes from, if we have a lot of certainty in our parameters, what's going to happen is that likelihood function is very steep. So there's lots of curvature, right? So what ends up happening is this number right here, there's lots of information, basically. It's really large, right? So our standard error gets really small. And when the likelihood function is flat, it's the opposite, right? So what ends up happening in maximum likelihood, we can turn basically our estimation process into the process that tells us about certainty because of this function right here. Anyway, it's cool stuff. I think that's neat. And then finally, how do we figure out the functions fit the data? Well, this is basically how you can figure out your log likelihood of your saturated model. Remember the saturated model where we're estimating all possible covariances, variances, and means, right? That's our first model comparison. There is something called a maximum likelihood fitting function, right? We could have the saturated model log likelihood. Different programs use this, different programs use a different version of it. Let me get to non-normality just a bit. There's another part I want to mention. If you're reading older versions of SEM textbooks, there's an equivalent likelihood function here that you may see that doesn't involve the mean vector. So in a multivariate normal, we know the distribution of the covariance matrix. Turns out the distribution of the covariance matrix, anybody? It's a guess. Statistics trivia. Trivia night at the bar down the street. No, it's called an inverse Wishart distribution. You're like, well, of course it's an inverse Wishart, right? Yeah, exactly. Just rolls right off the tongue. Why I say that is what ends up happening is if you read the older books, the very first way we did this was just to look at the covariance matrix and use that and maximize it. And that is why when I was describing the path diagram and the triangle was a late addition because we sort of forgot the means. In the original 1960s, 1970s Lisrel version, original Lisrel, not what it had become afterwards, you just need a covariance matrix, but it functions as still based on the multivariate normality assumption itself. Any questions? Oh my goodness, no questions. We're gonna have questions after break. Let's stop right there. I get so much into Wishart and I almost forgot break. Take a 10-minute break. We'll see you in just. That's right. Oh, there you go. That wasn't me this time. See you in 10 minutes. 10 minutes later. No, wait, 10 minutes later. Isn't that how the kids like to say? You know, the SpongeBob. I need to put those in my YouTube videos, but then I'm not monetizing YouTube, and I'm honestly, I don't know that anybody cares to watch. So my son will tell me all about how, Dad, you really need to edit your videos. And I'm like, kid, I don't have the time. But all right, that's right. The point is, the video is the fallback, or the if you didn't quite catch it, you can pay attention to the video so long as it works. But on that note, this appears to be working, so that is a positive. Okay, let's get back to it. So, what about us? We talked about how maximum likelihood works, and throughout this part, we've talked about normal distributions. But what happens if you have non-normal items? Well, first of all, our multivariate normal function assumed that the subjects and items are both independent. So people are independent from each other, and conditional on the latent variable, the items are independent. So remember that idea. Z is causing X and Y. Once we condition on Z, X and Y are independent. For us, the factor was what we're conditioning on. Item responses are assumed to be missing at random. That has a lot to it that I won't go into. But just know that that's a relatively better assumption than missing completely at random. So this is a good way of doing it, better than deleting data, deleting whole cases. We also assume that factor scores follow multivariate normal distribution. The item errors also have the multivariate distribution. And so when you put all that together, the factor and the items having normal distributions, if you remember the sum for each item, it's lambda times f plus error, and then there's a constant out in front. Because both f and error are normally distributed, they sum to become a normal distribution that shifts their mean and their variance depending on what happens with the part. So that's why we assume items are not multivariate normal to use this. But if we have non-normality, if we truly have non-normal item responses, what do I mean by that? Well, Likert items, right? 1, 2, 3, 4, 5. Our linear model predicting our item response function for the factor may not work well. Think of it that way. If y is equal to an intercept plus lambda times factor plus error, there's cases where that factor will give you predicted scores that aren't possible. In the case of like binary data, like zeros and ones, you can get predictions of probabilities greater than one or negative probabilities. And I don't know about you, that's really hard to do in a conceptual sense. The probability I flip a heads on this coin is 1.2 doesn't make any sense, just like it's negative 5.5 doesn't make any sense. Similarly, and more to the part of the Likert data, you might predict someone's expected response to an item is 3.5. That is not in the sample space of your data, meaning you have 1, 2, 3, 4, 5 for your outcome, and each person you might say, hey, 3.5, right? So you go outside of the model for different types of responses. Your standard errors, your chi-square based model fit statistics will be incorrect. Why are these incorrect? They involve a multivariate normal assumption for the likelihood function, right? The likelihood function gives you the standard errors. -2 times the total sample likelihood is your chi-square test statistic. Well, it is a chi-squared variable. That isn't true if you don't follow multivariate normality. So what are our 3 fixes? There are 3 fixes. One is robust maximum likelihood. We mentioned that in path analysis. That's for data that are still unimodal and symmetric, but may have too thick or too thin of tails. We call it kurtotic data, platykurtic or leptokurtic. The second is to transform your data. I don't like that one. Transforming data is common, I'd say still, but when you transform your data, you also transform the effects that may be present in your data. And that's why I don't like that. Right? It could be bad. And then finally, and then actually it only works for some types of distributions, basically logarithms.
In general, I expect, like a homestead as opposed to.
That's it.
Make sure I'm on the same page.
That's it. What we're looking, the real solution that we normally have to do here, unless we're in the platykurtic or leptokurtic world, is we have to use a different type of likelihood function. Now, factor model depends on what you define a model as. The model is pretty much the same, the data have changed, right? But we're going to do that next. I'll show you that with item response theory, or also known as item factor analysis, next week, or if we don't get all the way done with this, some week, I don't know, sometime this year, in the future. I always tell people like, when do you have time to do, blah, blah, blah. Somebody wants me to do something for them. When do you have time to do it? It's always like 3 months. Like 3 months is that limit of mine right now. Things look really good in 3 months. You ever have that? Then you get to 3 months, it's still another 3 months. So in 3 months, by then, we'll have discussed this. I'd like to feel that way. December 19th. That's what I'm thinking for many reasons. No, okay. So we talked about robust maximum likelihood before. Basically, it's the idea of the scaling factor. I'm not going to go deep into these slides. I'll give you some headlines for it, though. In M plus, you say estimator equals MLR. Actually, in Lavon, you have the estimator equals MLR. That makes robust maximum likelihood work. Now, it's again robust for data that are still symmetric, but platet or leptokurtic, right? And the nice thing about MLR is it doesn't cost you anything. When you use it, if your data are perfectly normal, your scaling factor will be equal to 1, and it will yield maximum likelihood normal estimates. But if it's not 0, or if it's not equal to 1, then it corrects your chi-square tests and your standard errors, right? So MLR, maximum likelihood robust method, is our default. Still, same thing with path analysis. I will say, many of you use Stata. There's your Stata slide. What if I told you, I think I've opened the program Stata once in my life? I kid you not. So you say, I'm sorry, but that's what I do. But there is, you have fewer combinations, evidently. There is an SEM function that has ML, but no MLR, it appears. So, okay. Sorry. You know about model fit, but let's talk a little bit about that in the context of CFA real quick. Because in the CFA model, we mentioned this in path analysis before. In model fit, model misfit came largely from the covariance matrix. Remember that when we went through the model fit investigation, we looked at residual covariance matrix. We saw, what did we do? We looked at the model fit indices, global fit. Then we looked at local fit. We looked at residual, like normalized residual covariances. And if we saw some that were bigger than a number, we looked at modification indices, right? But in the process of model fit, we had described where misfit occurs is largely the covariance matrix. And the reason for that is unaccounted for dependencies that are not part of the model. The same thing happens in factor analysis, right? So the mean of an item is captured by the intercept. And for simplicity, if we just think about this, where our factor here has a mean of 0, or a z-score method, so mean of 0, variance 1, if we were to say what's the expected or expectation for each person or for an item across all people, this would be equal to 0 because the expected value or the mean of the factor is 0. This component is 0 because the expectation of error is 0, mean of error, leaving us only with the item intercept. And why I'm saying that to you is really, unless you put constraints on your item intercepts, the mean part of the multivariate normal will not cause misfit, because whatever the mean is in the sample, our maximum likelihood estimator has a parameter specific to it. It means it'll just fit it. Here's your mean, the end. And estimating a mean is by far the easiest thing in statistics to do. Okay? Same with variances. The variance of y, we have to think about, okay, this comes from the algebra of expectations and statistics. I'll just read you the result, though. The variance of y for this model is lambda squared times the variance of the factor plus the variance of error. Now, to get to there, we have to assume a couple things. Again, the variance of the factor is 1. This thing is variable. So whenever you multiply a random variable by a constant, its variance shifts by that constant squared. That's where that comes from. Error has a mean of 0, a variance psi squared. Actually, a variance that we have to estimate for error. But to make this additive, we have to assume that error and the factor are uncorrelated. And we do assume that, right? That is almost always the case. If it were correlated, this would not be accurate. We need 2 plus 2 times it's the covariance between the two. But we're assuming that the covariance is equal there. And because of that, though, think of it this way. We have lambda squared plus the variance of error, making the variance of y. Lambda applies, the factor loading applies in the covariances, so it shows up in different parts of that matrix. But the unique variance, psi squared, this variance of error right here, that thing is an additive term. So you can think about what the algorithm is doing is it's trying to find lambda, and it's looking and saying, oh, well, here's my variance of y, here's what I thought lambda was, but I've got this term, I can just make the difference and make it equal. And that's what happens. So what I'm trying to mention by this is to think of it, that additive term for variance makes it so that we don't worry about variance misfitting unless there's some type of constraint on our error variance. We normally wouldn't do that, but we have it there. How are we doing? Okay, so covariance is where we have model misfit again too. Same as in path analysis, right? The covariances that we saw when we were doing what I called the tracing rules, like when we looked at what is the covariance matrix of our items as a function of factors, they were factor loadings and factor covariances depending on whether you were within the factor or across factors. So the covariances are where misfit is the problem. Again, just like in path analysis. So just like in path analysis, we have to think about sort of the baseline for addressing fit. Now, these are Lisa's slides. She did a great job with this. I'm going to go quick through them because you already know how to do misfit. If I said RMSEA to you, what number do you want it to be? 0.08 or 0.05, something like that. If I said CFI, you want that to be? That's it, right? 0.95 or above. So that's basically it again. But just remember, what we were comparing, I should have used this slide in path analysis. We have different models for the covariance matrix. For 6 observed items, we have the one where we estimate all the parameters. That's our saturated. We want it to fit as well as saturated. But then there's also the independence model, where there's 0 covariance in between. And our model is usually somewhere in between. So you see all the fit statistics. We've seen this before, our estimator and all this. But same 4 steps in addressing model fit. And let me just ask, are you comfortable with a lot of the the model fit is exactly the same. Same methods. Do you want me to go through this again, or can we just move? That's it. Yeah, keep a cheat sheet by you when you're doing that, some type of guide. But yeah, basically the numbers, where we look for the numbers, the process of understanding the numbers, identical. Why it's identical is we're still making that multivariate normal assumption. And actually, for the rest of this class, it will be that assumption. When you get out of it and you have no multivariate normal, problems happen. Or if you go into Bayesian, also a problem. Anyway, so we have global fit indices, RMSEA, CFI, TLI. This is my quick version. They talk about good versions of what it means. Actually, it turns out there's some recent things that Lisa's added that I like. What we call good is more nuanced than just less than 0.08. But again, I mentioned this in path analysis slightly. Your nuance may not apply depending on which journal you're submitting it to, right? If the editors are not aware, or if they have a different nuance, could also hit you. A good fit is easier with missing data. Go figure. A good fit is more complicated depending on the number of observed variables you have or indicators, right? And good fit is easier with lower reliability of your factor. Here's the funny thing about fit to me, right? If we don't have a lot of information in our data, so reliability being low being one of those cases, not a lot of items being there, not a lot of indicators, not a lot of observed variables, or what was this first one? More missing data. All of that is an indication that we have less signal in our data. And so what should happen in model fit is it should be the case that we have a hard time determining if it fits or not. Most likely we would say probably not. We're losing power to detect model misfit, is what I'm saying. So it says good fit is easier. Really what we're saying is it's harder to reject a null hypothesis in these cases. That's how I look at it, right? So there's more, what I will tell you is there is a newer version of this called dynamic simulation approach to model fit that you see people trying to make a thing out of. I think it's a good approach. It's just harder, and I don't know at what point you'll see it adopted in your field's journals. So I'm not dwelling on that now. But leave room in your mind to know that model fit is still evolving. The other thing I will note is there are such discrepancies by field over what model fit needs to be. How do I mean that? I taught a class a couple years ago on multidimensional psychometric models, of which factor analysis is one, but I wanted to make it IRT and other things as well too. And it's one of those exercises. I had the students in that class look at technical manuals of state assessments. So every one of our state assessments for accountability, in Iowa, we have something called the ISASP. Every state has them to get federal education dollars, like 7 or 8% of their budget. Most of those manuals, Erica, I think you were in that class, right? No, you weren't. You heard, what did you hear? You couldn't find model fit, or model fit wasn't for what they were actually reporting. That's crazy, right? I sit on a technical advisory committee for the state of Missouri, where we oversee their assessment. And the vendor is using model fit methods that are so far out of date. I make the point every meeting that, listen, there are faculty at universities in Missouri doing a better job with their evaluation than you're being paid millions to do. They have like a 10 million, I don't know how many millions of dollars their contract is. Many millions per year, no model fit. Psychometric instrument. Model fit's a validity argument, none of it, right? Or so far out of date that they've missed not one, not two, but 3 different iterations of new model fit statistics. So that's a measurement for you. And I tell that to you because we're paying for that. That's our money. That's taxpayer dollars. I hate saying it that way. It sounds so political, but yeah, you're paying for warmed up garbage. You should at least use modern methods, the standards that we hold science to. But all right, that's one soapbox. In other places, you'll find very stringent fit. Again, I think it'll vary. It'll depend on which journal you're looking at, what the training of the editorial staff happens to be, and who the reviewers are. So I can't give you great advice on any of that, but just be prepared. If someone says something about dynamic fit, come back to these slides and grab the reference. And I think some of the optional readings are references, so download those as well that happen as well. Okay. All right, did that. We did this. Okay, there are ways that we can fix the model itself. We can always do model comparisons. So if model doesn't fit, we have to do something with it. I guess technically you could just leave it alone and call that a sunk cost and quit wasting your time. That seems very cynical, and nobody really wants to do that. Plus, it's not good for your career or your PhD. So in the absence of that, we have to make changes to our model to make it fit better. In path analysis, we saw some of those changes involving residual covariances. In factor analysis, residual covariance is reserved. Remember, I mentioned this the last time. If we add a residual covariance, it means that there's something other than the factor causing the covariance between observed variables. And that violates our assumption of what it is that's this factor is measuring, right? The idea that our variable z, once we condition on z, the x and y get uncorrelated. Or another way of putting it, once we condition on f, that y1 and y2 become uncorrelated. That's a huge important part. And we can quickly make the model fit by adding a residual covariance between y1 and y2 if that's a problem. But now we can't just claim that f is the only reason that y1 and y2 are correlated, which is a direct attack of validity. Yeah.
But it is okay if we add the covariance between like latent variables, for example.
Yes. So if you're in, so most of the time we wouldn't have to add them because by default they're already contributed. But what you're mentioning is this covariance, the F1, F2 covariance at the top of this right here.
Okay, it's not going to be.
No, it's needed. You can't assume. I think any two related constructs in someone's mind are going to be correlated, and probably highly correlated for the domains you're looking at.
If you were to do the study that you're having to do for the work, it probably would be a good idea to have one latent construct for A, one for B, and then have a covariance for your model as opposed to the single that is described.
Yes.
Okay.
Can you just like point on this diagram, like one covariance we can do?
Yeah.
Just so I can
Right here.
Okay.
Yeah. Any type of covariance between the items, you can do it, and people do that.
Okay.
But what ends up happening, again, think of it this way. For this model to be true and meaningful, there has to be a relationship, a correlation. Let's just use correlation because it's synonymous with covariance. There has to be a correlation between y1, y2, and y3. If there's a zero correlation amongst all three, you would see zero values for those factor loadings. And zero values for the factor loadings means none of these items are related to this construct. So number one, we have to assume that there's some correlation. But number two, just like in basic stat, when there's a correlation between two observed variables, in our case, we have a third variable that is causing it. So what we're saying is the reason that y1, y2, and y3 should be correlated is purely factor one directly. You could make an argument using a path model notation if you wanted, because this is an undirected path. You could almost envision a way where you could, this is synonymous with a direct path. It does the same job as F2 predicting F1. You could almost say that F1 causes this directly, and maybe F2 is an indirect effect, like in terms of mediation. But that's as far as you go. So once again, F is the reason why Y1, Y2, and Y3 are correlated. And if for whatever reason you don't fit well and there's a residual correlation between, let's say, Y1 and Y2, you can quickly fix it with a residual correlation, which would show up as a double-headed arrow between this E1 and E2. But now you can no longer say F is the only reason why Y1 and Y2 are correlated. You put that parameter there, you're saying, yes, they're correlated. F doesn't fully account for it. And something else does, but I don't even know what it is. It's almost exogenous to the model itself. Does that help answer your question? Do you see the reason why I'm dwelling on this much? I don't know that I had the right words for 20 years to say this, but now I'm really putting this front and center in validity. Because again, a valid concept to make this is that conditioning on it fully removes the correlation between those variables. That is what we want a strong measurement argument to be. Otherwise, F is a contributing factor, but there's something else going on in your data. And that's why I always like to say, if you're going to put a residual covariance there, you got to call it, it's no longer this factor, it has to be factor and stuff. There, stuff. Got it? All right, so going back here. So yes, you can do a likelihood ratio test. Take a look at your log likelihood. But the ways that we can fix the model is a little bit more constrained in factor analysis, right? Because we can't add residual covariances. What can we do, right? yes, we can add error. You see people do this frequently, but again, I think that is not a good idea in a measurement context. Um, right? The other way that you can think about it is looking at your data and saying there's some other dimension going on in addition to this construct, this latent construct, right? What do I mean by that? Later in class, we'll talk about models that use something called method factors. For instance, if we would have a method factor, whenever I say that word, I usually almost always, and you've probably even heard me mention it prior to this, I will say, let's imagine that question Y1 and Y2 and Y4 are positively worded questions, and questions Y3, Y5, and Y6 are negatively worded questions. It is not as simple as we just go and take their Likert score, subtract the max plus one, no, subtract their Likert score from the max score plus one to reorient it. What often is needed is a factor that talks about the valence of the items. The positively worded items would have a positively worded method factor. The negatively worded items may have a negatively worded negative factor. Those factors are not things that we necessarily care about the individual, but they control for features of our design that we may have to control for that interfere with the process of measuring the individual. Does that make sense? Mainly the thought is this, like you've seen negatively worded Likert items, right? You can say, I'm having a great day, or I'm not having a great day. Those sound like the same items, just reversed. But in practice, and this is more of a empirical phenomenon, like a survey research idea, it's not a true reversal. It's not 100% reversed. It's a modifier of what you're thinking, and it needs a statistical control to modify it. And that statistical control can be in the form of another factor added to the model. So if your model doesn't fit and you see all of a sudden that there's high residual covariances between the negatively worded items, what that would indicate is that negative process of negating the item is causing more mental gymnastics or however in trying to evaluate a person for it. And that might indicate a factor. Now, that factor itself, you may not do anything with it. It may not get reported. You may not talk to people about it. But including it does two things. Number one, makes the model fit potentially. But number two, the information that would have been in those items no longer really applies to the factors. It takes that information, builds its own factor out of it, this hypothetical one that you don't see on the screen, making it so that you have less precision of measurement of those factors. And you might say, wait a minute, that's a bad thing. Yes, it's a bad thing, right? You want more precise measurement. But if you didn't keep it in, think of what happens. Your factors are overly precise. You're biased on your standard errors. You may be biased on where people are. So adding that factor helps give you a more authentic version or better estimates of this, even if they are more spread out or more variable. Does that make sense? It's an odd model fit issue. By the way, I can tell my brain is just not paying attention to the clock today. I'm just in my own world. So if I get too close to break, will someone just polite me, not even politely, just say, hey, yeah, I don't need polite. I'm wasting your time then. This is hard. It's hard to listen to me. It's especially hard to listen to me talk about this stuff. You need a break. I can just tell I'm really like, for some reason, really locked in. Like I have that flow to me for some reason, which is a great feeling. It just means I'm not going to pay attention. Even though it's right there, I could look at the clock and right here and right here. Anyway. All right. So what does that represent? Usually when model misfit happens, you have unaccounted for multidimensionality, whether it's relevant to what you're after or something that needs to be controlled for. So what I'm arguing here is that what we end up have to do is we have to add to our model. Basically, we have to go and add parameters and add that, make it more complicated to make it fit. So add that. when you add there, so it's interesting. This is a picture from Brown's book. I think this is one of the chapters that I had you read. So an error covariance. Imagine this right here. Imagine you have an error covariance. This is general social anxiety. We're always measuring bad factors. I want some good. I should be like happiness or Yeah, let's think of that instead of social anxiety. Let's maybe anxiety. Well, anxiety can be good and bad. I'm a highly anxious person, and if I take away the anxiety, I don't know how to live. So it's what fuels me. It's what got me here today. That being said, if we have error covariance between items 5 and 6, if we add that, it's actually equivalent to us adding another factor here. I wouldn't say equivalent mathematically, it's a different model, but it serves the role of it, right? Because the factor loadings that would be on this factor, and you'll note they're equal to 1 on this, mainly because it's a 2-item factor. We need to have 3, or it needs to be correlated. But those 2 items themselves may have been specific to public speaking. So now you've got 6 items, 2 of which somehow mention public speaking, which evidently is a phobia. Yes, I had it too. For whatever reason, I feel good about that now, but 20 years in my career, now I can say that. Lots of practice. This thing, public speaking, could be its own trait, but you don't have enough items to measure it, right? So you can do a method factor for it. Yeah.
When we add this other factor here, we have to take into account that with like is it the T method? I can't remember.
The T rule, the counting, yes.
The T rule. So we have to like keep that in mind
Yes.
if we can.
But think of it this way. In this picture, the ones on this diagram mean that we're not going to estimate its factor loadings. So when we don't estimate its factor loadings, we're not actually adding much complexity with that factor itself. We may have a factor variance we're adding, that's one parameter. But generally speaking,
It's like the same conceptualization of like for every factor you have like X amount. It's kind of like
it's very different. Yeah. And actually, let me talk a little bit about T rule in this as well. The idea that we have to count. In a lot of measurement models, we are nowhere near the limit of parameters we can add. So let's think of it that way. We saw before with 3 observed variables in a single factor model that our observed variable that we had perfect, it was 0 degrees of freedom, meaning just identified. Means we can add no more. And when we go to 4 variables, we had 1 degree of freedom, right? But pretty quickly, those degrees of freedom go up exponentially because the number of covariances there's pairs of, but the parameters are now item based. So the pairs go up linearly. So what I'm saying with that is we rarely need to worry about the T rule. The other part of it is with small numbers of degrees of freedom for that model comparison, right, small numbers of possible estimated parameters, model fit tends to fit. It's sort of like misfit by degrees of freedom. I know that sounds weird. It is easier to fit a model where your degrees of freedom have 1 than your degrees of freedom are 10. Because think of it this way, what's it trying to do? It's trying to stretch parameters to fit this covariance matrix. And it's saying, in your covariance matrix, there's 1 fewer parameter than you need. It means you've got a lot of basically slack in all the other parameters to sort of account for it. But if you have 10, like a degrees of freedom 10, that's 10 covariances that you're lacking. That means the other ones have to sort of be stretched in ways to account for 10 variables now. So when I say that, the places where you'd need to worry about the T rule, like when you have 4 indicators, tend to not need to be worried about because they tend to fit well. And so it's interesting, the fact that you asked it, I was like, yeah, why would you even think about it? I was like, part of my mind is like, why is she asking that? Like, it just doesn't make sense. Because when you get into this, you're like, oh, in a factor analysis, I don't need to worry about it. In a path analysis now, when you've got all these paths and whatever else, you've got a lot more complexity in the model, you do worry about it more. But in the factor analysis, it's somewhat of a much more simplified model in many ways. That makes sense?
yeah, absolutely. I'm thinking too hard about it.
Oh, no. I'm glad that you asked the question. It was just funny. It was that odd double take where I'm like, I'm just too into the weeds on this. I need to remember what it's like to learn it. But I'm really glad that you asked about the T rule, though. That's a really good question. Okay, so that's when you need to expand your model. You can also simplify your model. One thing that people like to always argue about, doesn't matter what the value is the factor correlation. right? When you build a new measurement instrument, one of the things that you have to establish is it's a different construct than other. Sometimes we used to call that criterion validity, and back in the day, right, or right where we would say how correlated is it something it should be. I guess discriminant validity is how uncorrelated is it with things that shouldn't be. Well, if you have let's say you have a two-dimensional solution and your factor correlation is like 0.85, you might say, is that really two different factors? And the answer might have to be yes, statistically, right? They're highly related, but this is where, like in the reviewer Rolodex of complaints, this always shows up because there's no answer to it. So that, from a statistical point of view, you may need two factors with a correlation that may be estimated to be 0.85, 0.9. But if you remove that, if you make them one factor, the model doesn't fit anymore. So that's a problem. The other thing you may end up choosing to do is remove items altogether. And this is what the focus of the homework is. Take items out of the analysis. When would you do that? Non-significant loadings. Believe it or not, that rarely happens for unidimensional items. I know it sounds weird. It can happen, but in practice, finding a zero loading is difficult. But yeah, you can take that loading out. I will say that having it involved there, that loading, the only way this would cause bad fit is if it were correlated with items that weren't measured by the factor, right? So in our 6-item example, items 1, 2, and 3 were a factor 1, items 3, 4, 5, 6 were in factor 2, right? If items 1 and 3, if the factor loading for item 1 was 0, effectively 0, but there was some correlation between it and an item 4 on factor 2, that would cause misfit. But if it's uncorrelated with all the items, leaving it in or taking it out will have a negligible effect because a zero correlation can be a zero correlation. Yes. Excuse me. Yes.
Would you want to test your model with, if you're thinking about eliminating one, would you want to see model fit and eliminate one, and then try with the other to see and say, okay, together compared to this one,
You normally,
that one, and say which one appears to be,
if you have a multi-factor solution and you have this,
yes,
you almost always have to compare it to the simpler where they're combined.
and then,
But then,
and say which one, if you have to,
yeah, that's right.
or
Yep. The other thing you have to do, if that's not, so if you if I combine them and the model doesn't fit, then the next remedy is dropping the item altogether, right? Dropping the set of items on that second factor altogether. That could be a remedy as well too. Neither of these are great situations, but they happen all the time. Yes.
Question on the negative loading. There's been a couple times that you mentioned reverse coding measured items is not good, or like, but is that what we do anyway?
Yes. It's most people will reverse code their item so that the loadings will be in the right direction. But what I was going with, not just reverse coding is not enough. How does that sound, right? I personally, whether or not if you know you have a negative item and you expect a negative loading, I don't see a problem with that. It's just by convention that we don't like seeing it in our texts.
Try to make that change.
Right. A mathematical argument for it would be why? Because if we reverse coded it, what we should see is the sign literally changes. But, what the negative loadings may actually indicate is that you might, when you see that, there might be something else going on. The other part of it is negative loadings also seldom happen on simple items. So items that only measure one trait. Because so many things are so highly related, positively related, you rarely see that unless it is a reverse coded number. Where you do see negative items, if you get more complicated factor models, we started to see it on the last slide. We will have a lecture about this later on, but we may have, actually, we don't see it here. But this is something called a higher order factor. It's very closely related to a bifactor model. A bifactor model says there's a general factor and there's a bunch of specific factors, but that means that each item may have more than one factor it measures. And in that situation, you can get negative loadings on one or more of those. But yeah,
So for the purposes of this case, we're not worried about negative loadings. We'll be fine.
I'm not. No. I feel like it's such dogma. Like people, back when it started, this is a dogma psychometric dogma. How's that sound? Like when we started psychometrics, that was a big deal because we didn't have the tools we have now. Now, it's just a loading, right? We know how it behaves. We know that more of that item means less of the factor. That's how we can recognize. Yeah.
Is that why a long time ago you would actually see it would have felt like the same question twice because people are trying to make sure that you are thinking the same way and then maybe you fit them all and you drop one
Yeah.
side and drop the other.
Turns out that that may have been the case, but that causes way more problems. We've known about that being a bigger problem than anything else, even from exploratory factors. So we could tell here in statistics, like in our model, that we can't have a 2-item factor, right? Because we can't estimate all the parameters. But if we have these 2 items that are super highly related, which is asking the same question twice, should be, that causes a whole lot of estimation problems for what we do. Because what'll end up happening is they sort of define the factor. Like that, they become they just become the whole thing. When really now you dwarf all the others. In the old days, old meaning exploratory factor analysis days where that's all we had, they called that a hidden doublet factor, 2 items measuring a thing. It's a really bad thing to do. So mathematically, when we have that, that's usually a huge issue. As to why, I'm not. I just do the math. Right? I don't know why. Sorry. Actually, that's my cop out to say I honestly don't know. I don't know the history of why we would have done that. But okay, I think these 2 why you might drop an item. Here's the big one: problematic leftover positive covariances. Whoops, right there. Those ones right there. You may not need both if you have a positive covariance between items. You may only need one. It's a indicator of 2 items doing the same thing, potentially, right? And what I tend to do is try to count up which items tend to have bad residual covariances and target those for removal. But here's the thing: when you drop an item and you want to look at how your model compares, you can't. Because all of our model fit statistics are based on likelihoods, and to make comparisons of likelihoods, either through a likelihood ratio test or through using information criteria, require you to have the same data with the same people. And when you've removed items, the number of observed variables has changed. You don't have the same data anymore. The model is now different. So you cannot go and do likelihood ratio tests or information criteria. If you really needed to do that, you had to set a loading to 0, but that test is so performative, it will always fit better, right? So that homework that you're doing, I make you drop items, but at the end, I'm not having you do a model comparison, right? You're only looking to see if that new model fits absolutely, not in a relative sense. But I will tell you that in practice, to me, unless you're in a case where it's very obvious as to you need some type of methodological factor to control for some design consideration, which is limited, more often than not, dropping items is your only recourse. In particularly if you're trying to build a unidimensional scale, one factor, because you can't add anything more to it. Right? And if you add residual covariances, now you're weakening your argument for the factor itself. So if your job is I need a measure of body dysmorphic disorder or someone's body dysmorphia, some of their feelings about what their body looks like, and you only want one dimension, you're pretty much left with removing items. Right? It happens. It stinks. It's hard, but that's life. Okay. What else could go wrong? I did look at my watch there. Oh, everything could go wrong. Ever seen the message non-positive definite? Yes. I see Erica's like, yes, you must be doing statistics research. And Lisa and I like to describe, and maybe those of you who do higher ed and student affairs, you probably can do this. Do they have a class on how to speak as an administrator? We call it dean speak. It's like, oh, like if you have an argument, someone says, well, they weren't positive about the idea. Like it's like a way of like speaking in neutral terms. You know,
There's no class on it. You just learn
I was going to say like, because I mean, like if you go into a meeting with a lot of administrators, not everybody, but you go to a lot of them, they're like, I mean, do you know what I'm talking about, right? They're like, oh, I didn't express, they didn't express their enthusiasm, or like they speak in these coded, neutral, like some of the business speak, but not like in academics. You know what I'm talking about, right? That's one of them. Oh, I'm non-positive. I'm not positive definite about it. Oh no, that doesn't mean that. It seems like it's dean speak, but it's not. It's actual. That is that's bad. What that means is you can't mathematically invert the matrix. I know you're like, why would I care about that? Well, it turns out the likelihood function cares. When that happens, you're working in approximations. That's my rough way of looking at.
you can't find your slopes.
You can't find your slopes. Your model is broken, and you can't keep it. I'll let Lisa summarize that. Right? You can just say that the dean was not positive definite about it, and move on. Right? That's how to say it. Whenever I see that, all I do is I think of, oh my gosh, I'm sounding like this is why I used to almost became department chair once, and probably would have failed badly at it because I just can't. I can only do that for so long, and that length of time diminishes. There's an negative autocorrelation per day. So at some point, I'm just like, ah. Anyway, there's also structural under identification. So you need a factor mean and the variance for at least 3 items. Does each factor have a mean and a variance? Of course it will, otherwise it won't estimate. And you need 3 items each, technically 2 with a correlated factor, but just need 3. Where this really shows up is if you have a marker item, remember you put a 1 for the factor loading to estimate the factor variance, but that loading, there's 0 correlation between the item and the factor. Because now you've basically taken that 0 correlation, made the loading parameter 1 out of it, and injected all this craziness into the system. So if you are using marker items and you get a non-positive definite message, change the marker. It can quickly make it work. By changing the marker, what we'll see in code is it just Lavon and M plus default to the very first item specified on a factor is its marker. If you change the order that the items are specified, instead of Y1, Y2, Y3, make it Y2, Y1, Y3, it changes the marker. And then finally, there's this other part, which we call empirical under identification, meaning you've specified it correctly, everything seems to work, but for whatever reason, we just don't have a lot of information in our data, right? We have a very small sample size, or highly variable data itself. But those are bad things. And so open in case of emergency. If good model fit seems hopeless, which by the way it normally is. Actually, I'm going to stop here. I just looked at my watch. I can't interrupt break. That is an emergency. So let's stop here, have 10 minutes, and come back and then talk about putting the E back in what we're talking about. Exploratory. Anyway, welcome back. 10 minutes later, something like that. All right. We talked about what can go wrong. I did, thank you. And I do see the audio bar flashing. In fact, oh, now you can't see it, of course. That shows me right, but yes, I can see it on my side. So hopefully that means it's being recorded. In case of emergency, this is really what happens. If good model fit seems hopeless, by the way, it often does. If you're trying to build an instrument using factor analysis, I've never seen it work off the shelf for a 10 item measure ever that I've run. I've run probably hundreds of these, if not thousands of these. With real data, it's hard to get to fit. So you may choose to go back to the exploratory drawing board. And this is where I will note that it's not exactly going to exploratory factor analysis. EFA sounds great in that you give the computer your data and it says, here's what all the loadings are. But it turns out to get all the loadings, boy, not good. You have to put some really weird constraints on the model to use maximum likelihood, or have to use some really weird matrix techniques that are somewhat unstable with data otherwise. So what Brown talks about and what I really think about is really doing an exploratory through confirmatory approach, right? And you can turn, so up to this point I've said, there is no such thing as exploratory versions of confirmatory, there's no such thing as an exploratory maximum likelihood factor analysis. You have to set constraints. Yes, but here's how you can estimate the most loadings otherwise. You fix each factor variance to 1, each factor mean to 0. So we have standardized all the factors. Then each factor gets one item that loads only on it, and the rest of the items can load onto all the other factors. And actually can go a little bit further than this with a little triangle of zeros if you have the factor pattern matrix, this crazy triangle of 0. But what that does is it estimates the most loadings possible in a confirmatory sense. Doesn't mean that it's a good idea. It doesn't mean that it's going to be all knowledgeable. But by estimating the most loadings possible, you've made it so that your model fit becomes as good as possible on your covariance matrix side. And then you can try to look at which loadings are statistically equal to 0 using p-values or so forth to come up with something that looks like your factor pattern matrix from exploratory factor analysis. And then from there, you can go and do the confirmatory model afterwards. But it's a tougher thing to do. Generally speaking, I prefer model modification. To do this approach, you're basically throwing out the information of how your first model would have misfit overall. And there's good information in that, right? You can see residual covariances to see where the misfit's happening. I think a combination of approaches is really there. Technically speaking, hang on just one second, I'll let you say this one comment. Technically speaking, fitting a model, showing it doesn't fit, and doing anything else is kind of exploring. Yeah, it didn't fit. The end. Jane.
If we were ever to do this,
Mm-hmm.
how do we decide which factors load to which? Like, is it the one that loads?
So in this case, what I would tend to do is try to zero out the non, look for the statistically non-significant, put zeros there, and see if you have a story afterwards as to what it means. It may not. That's the hard part. So this approach is difficult and is subject to other problems, right? What does it mean? Technically, we could even rotate this solution because we didn't really define these factors. I'd say this is like my preferred method is take your model and just tweak it until it fits, which is another version of exploration. But I think that is better because it's first of all going to be closer to why you designed your instrument in the first place. And it's second, it has breadcrumbs as to why it's not working. There's evidence there as to what's suggesting that's what's not fully working. This is playing on the limits of mathematics, I feel like. Similarly, let me think of another way that this might work. Let's imagine I have a really good fitting scale. Let's say I have 2 dimensions and model fits great. And I want to add maybe a new item or a new pair of items. You can do a similar approach there. You could say, let's just estimate both loadings. I'm not entirely sure which of my subdimension, my factors these load onto, but I have this really good solution from all of my data before. maybe I collect a new set of data, I have these new items, you could go and basically estimate each loading on each of the factors of those new items and try to understand that better as well too. So there's lots of ways that you can go about doing this. What you sacrifice with any of these approaches is the ability to, generalize a result, right? This is exploratory research. You started with a hypothesis that your model fit the data, that this construct was underlying your items. You've rejected that hypothesis. This is what you do next, right? So, questions? Does that work? All right. All right. So, in summary, model evaluation steps 1 and 2: assess global model fit, identify local model strain. I'd say misfit. You have good global fit, good local fit. Great, but we're not done yet. What? Lisa will tell stories about how she's worked with people. I think she had some type of executive functioning scale. It's like cognitive psychology, like based, where great model fit. All the loadings were close to zero, right? Meaning, what does that mean to have great model fit, but all your loadings are close to zero? It means your items are uncorrelated, right? You can't make a factor out of uncorrelated items because factors describe correlations. So check your loadings, say one factor model will fit both of these matrices equally, perfectly, right? Because the correlations are all constant, the variances are all constant, and these are correlation matrices, so of course they're constant, they're ones, right? So we can get a one factor model, but under this first one, remember the system of equations to figure out what the loadings equal correlations are, right? In this case, this is the product of the loadings. The product of the loadings equals 0.1 versus the product of loadings equals 0.8. You can tell that the loadings necessarily have to be smaller to give a 0.1. And actually, in both of these matrices, I'll tell you right now, if you had data that had this, you will find the loadings will be equal across all items. Because to get the same correlation in every spot, they have to be equal because the correlation is the product of the standardized loadings. So we know if the loadings are all equal, to get a 0.1 multiplying the same number together is different than to get a 0.8 multiplying the same number, and this one's larger. So that's what we're saying with that. So good model fit does not necessarily mean an interesting story or what you want it to mean. Good model fit means now I can interpret my results. Okay? Gotcha. All right. So effect sizes. So what are effect sizes and significance? So when we run this in Lavon, which looks like I'll be pushing that into next week as well too, I'll give you another week on homework. Fine. All right. Or have you looked at the homework? Can you do it? Mostly. Well, I'll get enough to be able. You can do it still in the week, and we can finish up next time. Inspect your parameter effect sizes. Well, turns out you can get an R squared for each item. Now that's a weird thing. I think I talked about it earlier in this lecture. You're predicting an item with something you didn't collect. How can you talk about the R squared? R squared is proportion of variance of the item that's in error, right? So yes, you're predicting an item with error, but that R squared is what's left over after you predict it. You can also get standard errors and p-values for unstandardized estimates to see if they matter. The other thing you want to make sure is that there is no weird estimates. So standardized factor loadings have to be less than 1 or no negative variances. By the way, in the old school days, an estimate of a negative variance in exploratory factor analysis was called a Haywood case. You may hear that term, Haywood case. That speaks to like an older era of science, a Haywood case, non-positive definite, all this other stuff. It is a little bit different, but you can find weirdnesses in estimators as well too. And then finally, this is one of Lisa's things that she likes doing, seeing if the CFA model should fit your data well, right? So what she did was, in this case, she looked at data where she had item responses that ranged between 0 and 100, like a slider bar. And she found that when you output the factor mean and made predictions, like if you gave everybody a factor and made like a y hat for each of these observations, you wanted the data between this light blue line and this dark purple line. But you'll see after a certain point, all the predictions exceeded the scale, right? See what's doing here. So once again, what she did was for each person, she outputted their factor score, which I'll show in a slide. And then with that factor score, she made a prediction for what this item response should be for each person. It was intercept plus factor loading times that factor score, right? Just like the equation would put. We know from the data that you have no responses that are bigger than 100 and no responses that are less than 0 on the y-axis. Yet the prediction for those factor scores, right after you get to be about a factor of 1, all predicted scores that were impossible, right? That is a problem. So what she's done, and she has syntax to do this, I think it's even in my syntax as well, to go and check. This is an assumption of CFA, right? That one of the ideas of CFA is to use this normal distribution that we basically keep our predictions in bound, but they don't. And this is what would happen if you estimated a linear model with dichotomous or binary data, right? You're going to have predictions that are out of bounds. What she ended up doing was doing a log transformation where she basically log transformed within the min and max. And then after that, she could show prediction stayed in bounds. But in a couple of weeks, we'll talk about that as a new set of models. Okay. All right. Then, finally, we're getting to the end of this here. There's a concept. So all of what we talked to this point in this class today has been about model fit relative to the data. Now we're looking at results. We want to talk about what's happening in our model. Really what we want to get to when we do a latent variable model, we often have to describe how much reliability the instrument has. Right? I kid you not, we could probably teach a whole class on reliability itself. It's a very esoteric and nuanced topic, and I'm pretty sure none of you would enroll in it, but that's okay. One of you, maybe two, maybe, I don't know. Anyway,
If it wasn't a because reliability, maybe.
but reliability, we take the same idea that we started with on that week I wasn't here, and I showed you Lisa's videos. You remember reliability was defined as the proportion of total variance accounted for, or proportion of total variance is described by variation of the trait, right? Right. So, or better yet, variance of true score over variance of true score plus error. Remember that formula? Okay. We need to do that as well. Here's the thing that's weird about reliability. Every reliability index has a name. Coefficient alpha, Spearman-Brown, coefficient omega, congeneric, and then there's other reliabilities that don't have a name. And then when you get into other measurement models, there's no constant reliability for certain scores. So before you even get into this, I want you to think to yourself, reliability for what? That's the first step, right? So what do you think? What do you mean, Jonathan? Reliability for what? Okay, reliability is important if you're giving someone a test score. So reliability for a test score. But there's multiple ways that you give them a test score. Most times you just add up the number of items. The classical test theory add things up. When you look at reliability for adding things up, that's where you get into things that are like Spearman-Brown, alpha, or omega, right? So reliability for the sum of items. Now remember, the sum of items is not from our model. That's not F. So I find that to be a little weird, but let's talk about it a little bit. Sum score reliability is an interesting feature. We will, a lot of times in factor analysis, people will use factor analysis to describe the fit of the model. Or another way of putting it, they want to make sure that your factor or factors fit the data because that is a check on the right dimensionality. Because in a regular sense, if you didn't know a factor analysis, if you just added up a bunch of items and you made one score, but you needed two, that's a problem, right? So now you just combine both effects into one, it's not a good idea. So factor analysis, for a lot in many people's eyes, is a way of describing dimensionality of your data. But then you're going to go and turn around and give somebody a sum score for their result. Seems a little unsatisfactory, but it happens. In that case, reliability is something called omega. And actually, here's the fun thing about reliability. I can't believe I'm going to do this, but I'm going to. What we could think about there is the following. If we're taking the sum of items equals 1 to the number of items of y sub I for a person, right? So in this case, person and item, we can go and trace out the idea of reliability this way, right? Remember, reliability, what we're looking for is reliability to the true variance of the true score over the variance of the true score plus the variance of error. Remember that? This is some version of reliability. Omega, alpha, and Spearman-Brown, all of these make different assumptions about how we get each of these variances right there. Okay? But they all stem from this one concept, which is we have the sum of items. Well, that's like saying we take the sum of items equals 1 to I of what our model happens to be. In this case, it's mu. Let's just say we have a one factor model. Right there. Now, we can do a little math and substitute or take this sum that we have in here, distribute it. We end up getting the sum of mu plus, now I'm going to take the constant out, lambda times the sum of the factor right here. And then we get the sum of error right there. Okay? Right? So now, what we can talk about is what is the variance of this. And when we get into the variance, like what is the variance of this total score? Because that actually gives us these two components down here, that total variance. When we do that, we can see a couple things. The sum of mu, so let's do this variance is going to vary here. The sum of mu itself is the sum of a bunch of constants, right? Adding constants to something that's a variance doesn't change the variance. It shifts the distribution, but it doesn't change its scale, so it doesn't change its variance. So that part goes away. What we're left with is lambda squared times the variance. And actually, in this case, I did this a little bit wrong, didn't I? It is the sum, oh my goodness, the sum of lambda I times the factor itself. And in this case, we get the sum of lambda I times that factor. We can just separate the two of those. And so what we end up getting here is the sum of lambda I squared times the variance of the factor, right? Because anytime this factor is the variable, and anytime we multiply a variable by a constant, we have to square that constant that does that. And then over here, we have the variance of error by itself. This thing, if we set to 1, let's just imagine we standardize factor. And then this thing is described by a parameter lambda squared. And actually, in this case, this is me doing impromptu again. I should learn. This term at the end is actually the sum of the error terms. So we have to apply the variance function to the sum of it. If these variances if the items are uncorrelated, no residual covariance, then this happens to be the sum of the variances parameters themselves. So what I'm getting at here is if you look at these two parts of the model, this up here deals with the true score. This is the variance of error. And in the factor analysis model, that's how we actually can calculate the sum score reliability. Right? The sum score reliability, I made my factor score 1, but the sum of lambdas squared times the factor variance is our variance of true score if we summed up the items. And the way you can think about why this is for a sum score, look, there's a sum in this formula. This is for a sum score. Okay? The error variance is the sum of the error variances down here, that term. Now, in Lisa's slides, she's allowing for residual covariances. So if you have residual covariances, it actually reduces your reliability. That's what that's saying right there. But what this is telling you omega is your coefficient of reliability for a sum score under a factor model where there's no constraints on the item parameters. And remember, it's a factor. It's for the sum score. How are we doing with that so far? So why I want to say that is I mentioned two other ones, Spearman-Brown and alpha, of which I'm pretty sure everybody knows alpha. You've probably had to hear Spearman-Brown, but Spearman-Brown went by the wayside. It turns out Spearman-Brown, or alpha, is this formula, but instead of having each item have its own factor loading, all factor loadings are held constant to be equal to each other. That is the assumption that we call tau equivalence. So if we set a constraint on our model to say factor loadings are equal, we get coefficient alpha out of this formula. And for Spearman-Brown, it's a parallel items assumption, meaning all of our residual variances are set equal to each other as well too. So why I'm saying this to you is what you've had to learn about reliability when you had to learn about coefficient alpha was our knowledge of reliability up to 1954, right? That's the paper. This is the most cited paper in Psychometrica, Spearman 19 or Cronbach 1954, right? That's a big paper. The modern version of reliability has to start with reliability for what? Okay, a sum score, great. Here's reliability for it. Now you might be saying, wait a minute, why am I doing a sum score? Turns out if your model fits the data, in factor analysis, the correlation between the sum score and your factor score is very high, 0.95, 96, 98, something along those lines. So if your model fits your data, using coefficient alpha is probably not that much of a degradation of your reliability. So that if has to be there. Your model fits the data. If your model doesn't fit your data, you're going to overestimate reliability. And you can see it with this formula, right? If your model doesn't fit your data, it means that one of these residual covariances is not zero. And once you account for it, even if you shouldn't, you diminish reliability. So, now, what about the factor score? How are we doing, by the way? This is a complicated concept. Spring it on you at the end of class here. Not a great idea. I'm going to extend homework one more week. Okay? Okay. I don't know if... Yeah.
I saw you got masters in statistics, so this feels like a really stupid question for me to be asking.
No stupid questions.
But what if those two just cancel out? Like
This part right here and this. So the denominator doesn't work that way, right? So if you took the inverse of this, if this sum was over that, then that you could break the sum into parts. But this doesn't cancel out. No. Yep. Yeah. So when you have the sum on the denominator, you can't cancel terms with it. You have to do some other algebra to see if anything cancels. In this case, nothing cancels. Yeah. Yeah. No problem. But again, thinking about where reliability comes from, why I did this derivation for you here was to get you thinking, oh, we started with a sum score, but we put a model on that. So we just put the sum of our model together, and that gives us the concept of reliability for the sum score. But another thing with this reliability. So number one, why people do sum scores in factor analysis is usually a high correlation between the sum score and the factor score with normal data. Now, if your data aren't normal, it doesn't hold as much. If the model doesn't fit, it doesn't hold as much. But second, the other thing to note about is reliability is per factor. So I've seen it happen before. Heck, it's happened on some of the papers I've submitted. You have a three-dimensional scale. You submit it for publication. The editor says, I need your alpha. I need your coefficient alpha. And you provided 3, but I want 1. That's a problem. Remember, reliability for what? I've established that 3 dimensions fit this model. So if I gave you 1 score, I'm not going to have a calculation of reliability for it because that's not accurate. We don't have 1 model. We don't have 1 score, right? So every factor has to have a reliability in your model. There's not reliability for a test. It's reliability for the dimensions of the test. Does that make sense? Okay. Now, let's talk about the other part of it, which is why don't we just use the factor score? Because the factor score is part of our model. And we can. That's why we use GRE scores. That's how we use test scores in a lot of different areas. In that case, we could still calculate reliability. It's a little bit different. But the other thing we get to when we look at the factor score is that each item is providing us quantifiable information, a statistic called information, that describes how much information that item contains about the factor it measures. It's a concept called item information. And item information for each item, you can calculate if you have a unidimensional item, it is the loading squared over the unique variance. What that tells you is which items are more informative about the factor. Remember, the loading was the covariance between the item and the factor itself. This is like saying squaring that covariance, but also like controlling for how much error was left over in the item itself, right? And that error term is good because sometimes the items may have different metrics. You might have a 5-point Likert item, you may have a 7-point Likert item, they'll have a different variation. That's why this shows up. So what this tells you is which item is best at measuring your error factor. Okay? So item information is useful in figuring out, if you have a scale, let's say you have a survey with 100 different items, and you want to cut that and rely, and first of all, you're in the fantasy world where it fits, and there's a unidimensional measure. Okay, great. In which case you might say, I need to figure out the 10 items that are most informative, right? You likely won't just use the statistical criteria, but you want to make a short form. This will tell you which items to select. You can calculate this for each item that you have. In factor analysis, item information is constant, meaning you have one number for the factor. Or another way of putting it, it is not conditional on what the value of the factor is. In normal factor analysis, normal theory, when you assume normal data, put it that way. Any other distribution for your data, and that's not true. How many of you took the GRE before you got to grad school? You've done. How many of you taken any other exam with a computerized adaptive assess? The MCAT. What is the business one? GMAT. GMAT. Those? Any of those? Anybody? Turns out those computerized adaptive assessments use item information to figure out which item you should get next. But because they don't use normal assumption of normal distribution, they use Bernoulli or discrete data, each item now information is conditional on the factor. So depending on where your point of the scale you are, some items will be more informative than others. Think of it this way. If you're a really smart student, which you all are, here in grad school, took the test, getting an easy item, like a low difficulty item, will not provide much information about your factor because you're most likely going to answer it correctly. Right? Getting a very hard item is what you need. Right? So the computerized adaptive assessment says, I'm going to calculate at each step, each item every item information conditional on what I think your factor score happens to be, and give you the most informative item at that point, thereby shortening the assessment for you. That's how computerized adaptive assessment works. But here's the fun thing about computerized adaptive assessments. You can't do those with CFA because they would all be the same. Your order would always be the same. It doesn't matter what level your trait you have. The most informative item is always the most informative item. The least informative item is always the least informative item. We'll talk more about this in the weeks to come. Item information is why people say, I love item response theory. Turns out there's some catches to it. All right, so that's one thing. And the other part of it is, how do we calculate reliability for the factor score itself? Well, it turns out that one is a little bit more complicated. Some ways we can calculate it from output, but if we go back to our definition of reliability, again, reliability is variance of true score over variance of error. What we know is the variance of true score. This right here is the variance of your factor, or I guess in Lisa's notation, sigma squared f. And we set that as a marker term. The variance of error, this is basically, we can calculate it. If we get this, your factor score, it usually comes with the standard error, and we can square that standard error. It turns out in factor analysis, if everybody gives you the same, if there's no missing data, everybody will have the same standard error. So in that case, reliability for the factor score is also constant. Yes. Yep. So reliability is a very important concept, but it's often not well understood, even from those who do it for a living. But just remember, reliability for what? If you hear omega or alpha or Spearman Brown, that's a sum score. If you hear something else, it's a factor score. Sometimes omega is called congeneric. I don't know why, but that's the term. When you estimate all the parameters, it's congeneric. All right. In Lavon, if you wanted the factor score itself, you can get, we can actually do this, and I have this in my code. You can calculate your reliability in any one of these ways, with the exception of the reliability for the factor score itself. But the sum score reliabilities, you can calculate it directly in Lavon, have it output, and not only does it output the reliability, it also outputs the standard error of reliability. So you can get a nice confidence estimate in how reliable your measure happens to be as well. But last thing on this note, what makes reliability higher? You can see it in either formula. I'm going to talk about it from item information, but you can see it down here too, right? Turns out, actually, I'll talk about it down here. Reliability is high when what happens? Factor loadings are large relative to unique variance or any other model misfit. That's the key, right? So how do you make a more reliable assessment? You find items that measure the factor better. If you add, what happens to reliability if you add an item that has a 0 factor loading? It'll go down because it still has a variance, unless it's constant, right? So in a more, I don't know, organized semester, I'd probably spend some more time on this, but there's the factor score reliability formula right there as well too. Okay. Any questions on reliability before I move on? All right. Then, in summary, the primary advantage of working in CFA or a measurement model framework is obtaining the model fit indices. It's a much more powerful method. Think about the other methods that came beforehand. Exploratory factor analysis had nothing of that, just loadings and eigenvalues and whatnot. I guess modern exploratory factor analysis can give you versions of that, but they're still not as informative as the model-based method. You can talk about effect size and significance of model parameters. You can do nested model comparisons. And using everything in maximum likelihood protects you for missing data, and it has good large sample properties as well, too. You can test classical test theory assumptions in factor analysis, believe it or not. So for instance, for you to use alpha's reliability, I just mentioned you have to have all your loadings equal. You can fit 2 models, one with equal loadings, one with not, do a model comparison and see if that holds. If it doesn't, alpha is not an accurate measure of reliability. Now, it's probably going to be close, though. Here's the thing that really gets me, though, and I mentioned I was going to bring this week. It looks like next week I will bring you, I think I said the words, I will inject into this class this idea of how we look at equivalent models. I like this. If you go and fit a factor model where all the loadings are constrained to be equal and all the unique variances are constrained to be equal, that is a classical sense called a parallel items model. Each item is supposed to function differently. It's the same with respect to variance and covariance. When you do that, the factor score and the sum score have a perfect correlation. And I'll show that to you next week. That makes me believe that the parallel items CFA model, while not identical to the metric that the summing of items is on, but we can use that as a proxy to test whether we should even sum up items in the first place. Because if that model doesn't fit, then our sum score has a problem with it. Now, maybe highly related to our current score, but what happens when you use a sum score and you probably shouldn't, even if it's highly related, you start to see the ordering of people change, right? So if you had fit a model where you didn't have this constraint, basically, where you estimated all the parameters, that to me is the most natural ordering of people. That's our goal in psychometrics, is put people in order from highest to lowest. If you make these model constraints and model fit gets worse, you'll flip the order for some people. Their scores may be very close, but if you have a thing where you're saying the top 20% get into, extra training or remediation or who knows what it is, like a lot of times we have to make, that might change who gets in based on how accurate your model fits. Not often, but it does happen. So I like the idea, and I haven't done a lot of research on this yet, but not research. I haven't done a lot of writing to sort of get this idea out. Some people have, but I honestly think we should teach you factor analysis in a classical test theory class to set up a place to test whether you should even be summing things in the first place. Now, that makes all the other psychometricians' heads explode. You should see the camps of people. I mentioned psychometric dogma, like this idea, these ingrained truths that we seem to have that somehow need to be questioned sometimes. If you want to go to a psychometrician and be like, yeah, I can test classical test theory, most of them will be like, no, you can't. It's not even a model. What are you talking about? But I think it should be. I think we should talk about it. All right. So in wrapping up, the big picture of CFA, the unit of the analysis is the item. You're doing a bunch of linear regressions. And because item responses are included, items themselves they're allowed to vary in their item discrimination, their factor loading. Item difficulty can be different per item, although we don't really worry about that when it comes to model fit usually. And if you want to make your assessment better, more accurate, however, you can't just add items to it. That was one of the things in Lisa's video I think I had you see when she talked about how you make a test more precise in classical test theory. More items, because it's fuzzy, because you're not making assumptions of dimensionality and you're playing on average correlation of items. So long as those items are somehow correlated, even if they're indirect correlation, adding them will make it better. But in factor analysis, you need ones with higher standardized loadings. Put another way, higher item information, because the same information that calculates a standardized loading is in the same order of standardized loadings mirrors the order of item information. Here, measurement error is still assumed constant across the levels of the latent traits. What I say by measurement error is that's basically we calculate how much measurement error by that index reliability. Right? Reliability is more measurement precision, so 1 minus reliability is measurement error. But because we only get one number per scale, per dimension, it's constant. In item response theory, that's not at all the case. We hardly ever talk about it as reliability in item response theory. We actually use a different term. Conditional standard error of measurement is what we usually there. So there we have it. The lecture is done. I'm almost out of time, so I don't even know I should even start the example. Yes. 79, yes.
Yeah, I mean, here it's when we look at an example, right? And you understand it.
Hmm.
And that's what I'm trying to clear about my thinking. So the first line of our text, there's a factor equal tilde.
Yep,
Equal tilde. That is what's being factor as a latent variable.
that is right. Yes.
I'm just
Yep.
making sure.
So that's the next Lavon command I'm going to teach you.
Sorry.
No, this is great.
I'm trying to do my head.
This is
You had show me. That's what I tried.
this is great. You know the tilde, right? So this tells us the factor score follows is a 1. Um, equal tilde is defining a factor. Now, don't take too much of this code into consideration. This is a very narrow example with a single item indicator that we wouldn't want to use. Really, let me see if I can find some syntax for it. Here, yeah. So here, if I wanted to create a factor, in this case, what is sit? I've forgotten it. But our factor's name is sit. The ability to sit down. I am high on that factor. Boom. 3 standard deviations above the mean on that one. How we define it is basically we have 6 items we've observed, sit 1 through sit 6. Some of these are reverse coded with an R, so you know where this is headed. What this line says is we're going to create a factor with the name sit. Equal tilde says it is measured by these 6 items. Now, one of the problems, one of my new annoyances with Lavon syntax is it looks like you're adding together these items. There's nothing about this that is anything like that. Right? If you didn't see the equal here, you'd think this is a prediction function of some variable named sit with the sum of these. That's not it at all. Not at all. It's the other direction. Okay? So when you see this, realize this is not what's happening. You're not adding up items to make the factor. In fact, I'm telling you, don't do that. That's a bad idea. But if you want to define the factor, equal tilde defines the factor. Double tilde still defines residual covariance or variances or covariances. Same as in path analysis. Single tilde will define the intercept or any other variables you wish to predict with. That is how it works. So it's one. So the fun thing about this is conceptually, measurement models are so much different because we're trying to measure something that doesn't exist. And so we get into things like reliability and whether or not what we wanted to measure is what we're actually measuring, validity, right? So it's a big, expansive topic, but when it boils down to the actual functioning of it, it functions almost the same as path analysis, with the exception of now once you've defined sit as a variable, even though you didn't collect it, if you want to make a path analysis out of this and you want to predict it or you want to use it to predict something else, you treat it as it was observed in the rest of the syntax. And it works the same. So if you have an outcome y tilde sit, you'd put in here. You'd build a path model that way. It's just you define your measurement model here, and then whatever the factor is, you use in other places. And that's what we're going to cover next week. We'll go through this example next week to get this, and I will make homework again, do 1 week later again. Okay? This, by the way, Lisa likes to say your score is out of 100 points total for the semester. And I go, it's a weighted average of all the percentage of your homeworks, because I don't know how many we're going to get through. Yeah. One. Yes. It may be one homework at this rate. Okay. Questions or comments about any of this? How are we doing? Okay. Anything else today? I can just stop it here. All right. You get 5 extra minutes. Hooray. Thank you. And I'm going to stop recording, but I have